Let's review. The concentration of a weak acid affects its percent ionization. As the acid concentration increases, percent ionization decreases, and as acid concentration decreases, percent ionization increases. And in a previous lesson, I used the analogy that the more people that show up to work, the lower the percentage that are actually doing work. We talked about that conceptually in an earlier lesson, and in this lesson we're going to use a calculation to verify this. So let's calculate the percent of HF molecules ionized in and the pH of a 0.1 molar HF solution. And there's the Ka value for hydrofluoric acid. So there's our equation for percent ionization. So we'll need to use this equation. We're looking for that bit of the equation right there, and we certainly know the value of the denominator. That's 0.1 molar. If we're going to find the percent ionization, and we know the original acid concentration, we're going to somehow have to first determine the hydrogen ion concentration at equilibrium, and then we'll use this equation to calculate the percent ionization. So what we're going to do next is going to help us find the hydrogen ion concentration at equilibrium. And we're going to use an ice chart again. The initial concentrations of these substances are shown here, 0.1 molar for the HF. We're going to assume initially that the H plus and the F minus ion concentrations are 0. Of course, some amount of the HF will ionize, which will produce, on the right side, some amount of H plus and some amount of F minus. Therefore, at equilibrium, we have these values, 0.1 minus X and X and X. And that term right there, that X, is the H ion concentration at equilibrium. And if we look at the equation in the upper right corner of the screen, there is the H ion concentration at equilibrium. So if we can find X, we're going to put it in the numerator and we'll be done. Let's write the equilibrium constant expression and substitute in the values and the variables. We have products in the numerator, X times X, and in the denominator, 0.1 minus X, and those are equal to our Ka. We talked in an earlier lesson that if this power of 10 on the K value is -4 or smaller, and when I say -4 or smaller, I mean -4 or -5 or -6 or -7, -8, -9, and so on. -2 and -3, you cannot use this shortcut. But if the power of 10 on the K value is -4 or smaller, then you can use the shortcut, which says that in the denominator, X is very tiny, so 0.1 minus something very tiny is essentially 0.1. So this is very easily solved for X. I trust you can do that. And therefore, we know now the numerator in this equation we started with at the top of the screen, 8.25 times 10 to the -3rd, divided by the original acid concentration of 0.1, that's 8.3%. We're also asked to find the pH, so let's take the negative log of the hydrogen ion concentration, 2.08. If we hadn't used the shortcut, these are the values we would have gotten. 7.9% ionization and a pH of 2.10. And the amount of error that's introduced, it's well worth it to use the shortcut if you can. Now we're going to do the same calculation. The only thing that's different is that we are working with a much more dilute solution. You can see that the concentration of this HF solution is not 0.1 but 0.01. So this is 10 times more dilute than the one on the previous slide. Everything else is going to be the same. There's our percent ionization equation. We need to calculate that. We know the original acid concentration. Let's make our ice chart. We're not going to write out the initial and the change lines separately. We're going to put them all in one line. Once we know what we're doing, it's okay for us to do that. The at equilibrium line would look like this. 0.01 was the initial, and then it goes down by some amount x. For the H plus and the F minus, the initial was 0, and it'll go up, that is plus x. And same with the fluoride ion. We're saving ourselves a little time by going right to the at equilibrium line. So we need to find that value. There's our Ka. Ka is the same no matter what the concentration of this acid is. The shortcut says that we can simplify the denominator. We're going to solve that for x. Calculate the percent ionization, which turns out to be 26%. The last slide, we had a solution that was 10 times more concentrated, and its percent ionization was only about 8%. So you can see that the more dilute a solution gets, the higher the percent ionization. And there's our pH. Again, we did use the shortcut. If we hadn't used the shortcut, if we had used the quadratic formula, our numbers would come out, as you can see, slightly different. There's nothing wrong with using the shortcut. It's certainly close enough for government work, as they say. Let's summarize. The calculations we've shown here illustrate the point of this lesson and the previous one, and that is, there is an inverse relationship between the concentration of a weak acid and its percent ionization. In this black box here, you can see we've summarized our results from this lesson. On the left, we have the more concentrated acid, 0.1 molar. On the right, we have the more dilute acid, the one that's more watery. And you can see that as the concentration goes down, the percent ionization goes up. We've also shown the hydrogen ion concentrations and the pH. And at the bottom, note that the hydrogen ion concentration does decrease with decreasing acid concentration, and the pH does increase, as we would expect.